All right, limits and continuity. So limits is defined a little differently in space and in multivariable calculus. So let's first off with the definition. Let f be a function of two variables whose domain D includes the points close to a and b. We'll talk about what we mean by close to a and b in a little bit. Then we say the limit of f(xy) as xy approaches some point ab is L in this way. So the definition is kind of similar to what we do in single variable calculus. Instead of x going to value, it's the xy variables going to a single point itself. Okay. Here's what's a little different when it comes to the portion. We always do epsilon delta proofs when it comes to space, and that's what makes it more difficult. Is so in this case, for every number epsilon greater than 0, there's a corresponding delta such that, right, so the square root, so the distance between that point and its arbitrary limit points is less than delta. Therefore, the absolute value of the function minus L is less than epsilon. Okay. Now that's the general proof or the general definition of what a limit is. What's actually going on in space? So it's a little different when it comes to a single variable calculus. So let's suppose we have something going on just in 2D, just to see, and you could abstractly make this in 3 dimensions. So let's go back to what we know, the xy plane. Okay? And we have some figure, right, that if you go to 3 dimensions, we get a surface or a solid. Okay? Now, what this is saying is pick a point xy here, somewhere on this portion. So this is my point xy. And this xy value is going to an arbitrary point, and this is, let's say this is AB. This is the point AB. Now, what this means by arbitrary close to A is, I like the word neighborhood more closely, because once you get into higher integration and higher mathematics, analysis, they talk about neighborhoods compared to actual, instead of the point to point. So what this is saying is, if I make a circle around the point A, B, right? So, and this radius of the circle centered at AB, we're going to call that delta. So that's a delta we're going to be looking for to solve for this. And what they're saying is, around this neighborhood centered at the point AB with radius delta, there's an xy arbitrary close to AB such that the limit equals L. Okay. So if I just translate this now to a function to the xyz plane, so remember the z plane just goes up, so let's suppose this is our z plane. The limit L, where this limit ends up being approaching L, so therefore there's a neighborhood again around the z axis where we have a buffer above and below, where this is the limit plus epsilon and the limit minus epsilon, right? There's this neighborhood that the limits that actually go to L. Okay? And that way epsilon is so small that, that subtraction is eventually just L itself, right? That's kind of the core components of what single variable and transform into multivariable. Now it's neighborhoods. Much easier to deal with neighborhoods than, seeing it get arbitrary close to it. I really don't like the word arbitrary. Okay. So we have a bit of an issue though. So when it comes to space and surfaces, the limits is not as straightforward as it's done in the past, where you just plug it in and call it a day, or make a box method or anything like that when it comes to it. So since we're in space, the xy is approaching to some point AB in multiple ways because of the function fy. Now remember, we talked about this, right? Fy, the function fy is not specifically, right? There's multiple paths to that point, and that's the key thing when it comes to surfaces in space. Is a path C could be different than path B, A, path C, and so forth, right? These curvatures go through all of it as well. Now, what I'm talking about is if I have a point AB, so here's my point AB. In space, I can have multiple ways to get here. I can have this direction, I can go this direction, I could do that, and I could do that. right, in all aspects. So there's infinite many paths I could choose to get there. The question is, when it comes to a limit, is do all the paths go to a single point? And that's the hard part when it comes to space, right, in 3 dimensions. So we have a little definition before we get into abstract theory, is if the limit as xy goes to ab of the function equals L1 for some curve 1 or some path 1, and also if we have the limit as this function goes to another L2 for a different type of curve, so for example, let's say call this C1 is our curve 1 or path 1, this limit goes to L1, and let's say we have this C2 here, this curvature, this one goes to L2, right? So 2 numbers. Now, if these numbers are different, then the limit does not exist. That's how we're going to apply limit does not exist. Okay. So by contrary, you kind of tell the limit will exist if they both equal the same number, right? So both paths go arbitrary to the same number. Okay. So why don't we try a couple of examples out so we can see what's going on here. All right, so let's show the limit does not exist using our portion here, right? So limit does not exist, meaning we'd have to find 2 different paths or 2 different curves, take their limits, and show that that the limit L's do not coincide, right? Do not agree with each other. Okay. Now, when it comes to limits and 3-dimensional space, we're always going to pick the 2 easiest paths to show. Now, what I mean by that is the easiest ones is we're going to take the x-axis and the y-axis. So in other words, the only paths coming from the x-axis and y-axis. Okay, so let's do the x-axis first. So this means if I go, here's the point 0, 0, the origin, I'm coming this way. So I'm picking the path going this way, literally on the x-axis. Okay. So that means I'm going to take the limit as x, y go to 0, and you just put 0, 0, I'll just put 0 because, the same thing, of x squared minus y squared over x squared plus y squared. Now, here's the thing when it comes to paths or curves, okay? Because we're only dealing with x, and we're only looking at as x goes to 0, I'm only plugging in 0 in for x and seeing what happens. So if I plug in 0 in for x, all this goes away, end up being y squared over negative y squared over y squared, which equals negative 1. So the path or the curves that coming from the x-axis equal negative 1, that limit. Okay, so all we have to do is show, since we don't want to show it doesn't exist, is if I do the other way. If I pick a different curve or different path, it's not going to be negative 1. So this time, we're just going to do the opposite. We're going to do the y-axis. So coming from the y-axis up or down. So again, kind of remember what we just did here. Taking the limit as the xy goes to now the y value. So if you want, you could look at it like this. If you like, x is just constant, so just keep it the same. And see where that goes. So now y's are just 0. We get x squared over x squared, which gives us 1. So therefore, L1 does not equal L2, so the limit does not exist. Okay. Now the hardest part is showing, does the limit actually exist? So that's what we're going to try to do here. So we have a couple questions to see out. Hopefully they don't exist. That's simply to do. If they do exist, it makes it much harder to deal with itself. Okay. All right. Well, let's see. So first example. And the best part is you can always use this template, the sheet, to see if it actually works or doesn't work. That's the nice thing. And so Let's do the same thing that I did above. We'll just choose the x-axis and y-axis and see if it does actually work out. Right. So first we'll use the x-axis. That means we're taking the limit as x, y goes to 0y of this. So plugging in 0 in for x, notice we get 0 on top, so we just get 0. Next we'll do the y-axis. And again, plug it in 0 for y. Notice you also get 0. So you're like, oh, sweet. This limit does actually exist. Perfect. On to the next. Now, here's the problem. Because we're in space, like I said, every curve must, and when we take the limit, must equal 0 now, right? Because we identify it's 0. So why don't we pick an alternative path? Let's say y equals x, because y equals does go through the origin, right? That's another path we can go to. Okay, so if we do that, and I'll just go xx, so now since y equals x of this function, well, that gives us x squared on top, and that gives me 2x squared on the bottom. This gives us 1/2. Uh-oh. And remember, every path must be the same, right? It isn't, according to the definition, it's arbitrary two paths. But every path, which means this limit actually does not exist because they do not agree with each other. So this is a no. Let's try the next one. And again, we'll do the same thing. All right, so plugging in 0 in for x, we get 0. Plugging in 0 for y, we also get 0. So if we were to get happy, we now know that we could have something that doesn't work, right? So what's a path you guys like? You could try this one, but, let's try something different. Let's try a third path, y equals x squared. Again, you could pick any path you like, right? Any along that goes through the origin. So now we take the limit as x, y now goes to x squared. So now plugging this in, so that gives me x squared y to the fourth, y to the fifth. And on the bottom I have, let's see, x squared plus y to the eighth, x to the eighth. Oh, this doesn't work, right? I have to find the limit. So, what if we just flip them? So instead of doing that, we now flip it to, oh, yeah, that will work. I could keep doing this, it's fine. Let's do that, there we go. So this is x to the third over 1 plus x to the sixth. Ooh, that gives us 0. Yeah, might be on the right track here. Okay. All right, so that one works. However, What if we just flip it? Okay, so now all I'm going to do is plug in x instead of x squared to be y squared. So this can be y to the fourth on top. Y to the fourth plus y to the fourth is equal to 1/2 after you simplify. Oh, great. So it looked like this actually could have been 0 unless it fails 0. Now the question becomes, do you have to check every single path there? No, you don't, right? It's much harder to show that it does exist than it doesn't exist, and that's the key thing. So I'm going to show you guys when one actually does exist, right, to make it easier for yourselves. So I'm telling you that 6 for C, it does actually exist. It does give you actually 0. Okay? And you can quickly prove it. Just plug in the x-axis and you get 0 for top and bottom. So this one does work. Okay. So if it does work, how do we actually show it does work? Okay. And that's, again, that's the difficult part because we have to use epsilon delta proofs to do so. Okay. So how does this proof go? So we're going to let epsilon be greater than 0. We want to find a delta that's greater than 0 such that the distance between the 2 points of x minus 0 squared plus y minus 0 squared, and that's the a and b in this case, is less than some delta, that same delta. Then the epsilon value of this minus 0 is less than epsilon. Okay, so that's what we want to show. All right, so we got to find some epsilon and some delta that would make this work. Okay, and just in case you guys forgot, it's been a while, you always start here and eventually find your delta and your epsilon. So we're going to start here. So the epsilon value of this minus 0 is just itself. So let's start here. Okay. All right, so since x squared is always positive, this is always positive, that's always positive, so that's going to be positive. So the epsilon value doesn't work there. So 6 is, again, still positive. So the only thing that really arbitrarily changes is this y on the very top. Everything else is pretty much broken down. Okay, so now that we have this part going on, let's kind of tweak what we have. So remember, we want to figure this is somehow less than some epsilon. So we got to start with some inequality. So let's start with this one. So we know x squared is less than or equal to x squared plus y squared, right, for sure. The only time it's equal to is if y squared or y is 0. That's the only time. So we know for sure it is greater than 0, or greater than itself. Okay. Now, somehow we have to make it look like this, right? So let's bring this over. So just divide it over. So now this is less than 1. Okay, so the only difference now we have on top, we're going to multiply both sides by 6 in absolute value of y. So I'm going to multiply both sides by 6 times the absolute value of y. We now have that. Okay, so from here, let's take a little note. The absolute value of y is the same thing as y squared. Or, sorry, the square root of y squared. Okay. Now here's the thing. The square root of y squared is actually less than or equal to x squared plus y squared inside the square root. Right, for the same concept we have above. Just taking the square root of both sides, we get the same result. But now we're just trying to get rid of the y value there. Okay. So therefore, by default, what's happening is now we have all of this is less or equal to this part, but this part was less than equal to that, so that's equal to 6, and just if you want to substitute it, all of this. Okay. Now notice that's exactly what we wanted, because if I just get rid of the zeros, that's a square root of x squared plus y squared. So we're going to let delta equal epsilon over 6. Because that's exactly what we're done. We got it done here. And why divide by 6? Because we divide over, it gives us the actual by itself, right? That's what we wanted. So let delta equal epsilon over 6, and let 0 be less than the square root of x squared plus y squared is less than the delta. Then we just work our way backwards. So this part equals this. Which is less than or equal to this. And we know this right here is sigma, or less than or equal to sigma. So we know this is less than or equal to 6 delta, because it's right, where's it, right here? We know that's less than delta. So we know this portion is less than this. And then we plug it in. So less than 6 times epsilon over 6, which gives us epsilon. And then we're done. So like I said, showing limits exist is much harder than showing that they do not actually exist. And the last part is very straightforward. It's continuous. Everybody loves continuity because this is everybody's favorite. You just plug and chug. So continuous, a function f of two variables is called continuous at a and b if the limit of the function is the same as if you just plug in the values of a and b into the function. Now here's a keynote. All polynomials, which is mostly done on surfaces, are continuous. And all rational are continuous as long as the denominator does not equal 0. Okay? And rationals is fractions, right? So all fractions are the same as long as the denominator does not equal 0. So therefore, here's a fun little example. Does the limit exist of this one? And absolutely yes, because as long as it's continuous, the limit does actually exist. So yes, it does exist. All right, and if you want to find it, you just plugged in 1 for x and 2 for y, and you could actually find the limit itself. B. Now what if we have a piecewise function? Okay, so we want to figure out, does this piecewise function exist given at the space intervals of that? Okay, so does this true is the question. Okay, that's what we want to figure out. So let's do each one individually. So let's just look at the top. So does the limit of that exist? Okay. Well, we actually proved that it didn't exist, right? But if you're not, you can always go back and just revert it. So you have to do it the long way. and see, does this actually exist? Okay. Now this is not bad because it's essentially 0 whenever that, so you know this portion is good. Now, here's the issue, because this actually ends up being interesting 0. However, oh, no, sorry, this is actually 0. However, is it actually continuous at the point itself? Meaning, does it skip? Okay, and that's the interesting part. It actually skips around. Remember back to what the continuity means, right? So it's continuous if the limit does actually exist given plug it in, right? So if I plug in 0, 0, I get something that's undefined. That's no bueno, right? Something that's undefined means the limit does not exist. So no doesn't equal that because the limit is undefined at that point or does not exist. Right? You can't actually find it. You can plug them in, right? The actual limit, but you can't just plug it in because it doesn't work out. So little trick question there. And the last one, same process. Now we actually showed this limit existed in the previous example. The only difference is this is a 3 instead of a 6. So we know this actually goes to 0. This limit does exist. And we know this one is 0 because the limit of 0 goes to 0. So we know that the points, any arbitrary points, does actually go to 0, 0. We know the limit does exist. So we know this side does actually work. And if I plug in 0, 0, do I actually get a value up? Do I get something in the portion? And yes, it actually does go through the origin. So yes, it is continuous. Since does give me f of AB. Or, the limit I messed up a little there. So this is a yes. So it is continuous.